Right now, while you're watching this, something extraordinary is happening above you. Our galaxy is transforming, not slowly, not gradually, but right this instant. Stars are igniting in clouds of gas scattered across spiral arms. Dwarf galaxies millions of light years away are being torn apart by gravity's patient grip. Vast rivers of hydrogen are spiraling inward through the darkness. The Milky Way isn't some frozen photograph from the ancient past. It's under active construction, and the scale of what's happening would take your breath away if you could see it all at once. When ancient peoples looked up and saw that pale river of light crossing the sky, they wove stories to explain it. The Greeks imagined spilled milk from the goddess Hera. Norse mythology called it the path warriors took to Valhalla. Chinese astronomers named it the Silver River. None of them could have known the truth. That faint glow, that delicate band of light, is our view from inside a rotating disk of several 100 billion suns. We're seeing it edge on from our position 26,000 light-years from its core, like standing inside a spinning coin and trying to see its full shape. The breakthrough came in the early 1900s when Harlow Shapley mapped globular clusters and realized something unsettling. The sun wasn't at the galaxy's center. We were out in the suburbs, nowhere near the heart of things. Then Heber Curtis and Edwin Hubble proved that fuzzy nebulae were actually separate galaxies, millions of light years away. The Milky Way was just one island universe among countless others. But even after these discoveries, astronomers assumed galaxies were essentially static. They formed, they settled into stable structures, and they coasted through cosmic history like ships in calm water. They were completely wrong. In 1970, Vera Rubin published observations that would shatter our understanding of galaxies. She measured how far stars orbit at different distances from the Milky Way's center using spectroscopy, analyzing the Doppler shifts in starlight. The results made no sense whatsoever. According to Newton's laws, stars farther out should orbit slower, just like planets in our solar system. Neptune crawls along at 5.4 kilometers per second, while Mercury races at 48. That's basic gravity. The farther you are from mass, the weaker its pull. But Milky Way stars didn't follow this pattern. Stars 40,000 light-years from the center orbit at roughly the same velocity as stars near the Sun, around 200 kilometers per second. This was physically impossible with visible matter alone. There wasn't enough gravitational pull from stars and gas to hold outer stars in such fast orbits. They should either be moving slower or flinging themselves into the void of intergalactic space. The solution revolutionized cosmology and changed everything we thought we knew about the universe. The Milky Way must be embedded in a massive halo of invisible matter, providing the extra gravitational pull that holds everything together. This dark matter, which doesn't emit or absorb light, extends perhaps 300,000 light-years from the galactic center. It outweighs all visible matter by a staggering factor of 10 to 1. The Milky Way contains roughly 1 trillion solar masses of dark matter, compared to perhaps 80 billion solar masses of stars and 10 billion of gas. Dark matter isn't just some minor addition to galaxies. It's the fundamental scaffolding, the invisible architecture that makes everything else possible. The dark matter halo collapsed first in the early universe, creating a gravitational well, a cosmic bowl. Then ordinary matter fell into this well over billions of years, collecting at the bottom like water filling a basin. Without dark matter, galaxies as we know them couldn't exist. The gravity from visible matter alone isn't strong enough to capture and hold gas over the immense timescales of cosmic history. This has profound implications for how galaxies grow. When we discuss the Milky Way adding mass, we're really discussing ordinary matter falling into a pre-existing dark matter structure. The scaffolding was built first, long ago. Now we're watching the building materials arrive and assemble themselves into the visible galaxy through gravity's patient, inexorable architecture. Before we can fully understand how the Milky Way grows, we need to understand the life cycles of stars. Because stellar evolution is intimately connected to galactic growth in ways that might surprise you. Stars aren't just passive points of light scattered across the darkness. They're factories for chemical elements, cosmic reactors that transform simple atoms into complex ones. And ultimately, they're the sources of the heavy elements that make planets and life possible. Stars form when molecular clouds collapse. These clouds, the coldest places in the galaxy at around 10 to 20 degrees above absolute zero, contain primarily molecular hydrogen with traces of heavier molecules like carbon monoxide and water ice. When a dense region within such a cloud becomes gravitationally unstable and begins collapsing, it fragments into smaller clumps. Each clump that contains at least 8% of the Sun's mass can potentially become a star. As the clump collapses, gravitational potential energy converts to heat. The center becomes progressively hotter and denser, glowing brighter with each passing millennium. When the core temperature reaches roughly 10 million degrees Kelvin, something remarkable happens. Hydrogen fusion ignites. 4 hydrogen nuclei fuse to form one helium nucleus through a process called the proton-proton chain in low-mass stars, or the CNO cycle in more massive stars. This fusion releases energy according to Einstein's famous equation, about 0.7% of the mass converting to pure energy. This energy creates outward pressure that halts the gravitational collapse. The star reaches what astronomers call hydrostatic equilibrium, where inward gravity perfectly balances outward pressure. It settles onto the main sequence, where it will spend most of its life steadily fusing hydrogen into helium. For a star like the Sun, this main sequence phase lasts about 10 billion years. For massive stars 10 times more massive, it lasts only 10 million years, barely a cosmic heartbeat. For tiny red dwarfs with just 10% of the Sun's mass, it lasts trillions of years, longer than the current age of the universe. Eventually, inevitably, the core exhausts its hydrogen fuel. What happens next depends critically on the star's mass, and the differences are dramatic. For stars less than about 8 times the Sun's mass, the core contracts and heats up while the outer layers expand enormously. The star becomes a red giant, sometimes swelling to hundreds of times its original radius, large enough to swallow inner planets whole. The core temperature eventually reaches 100 million degrees, hot enough to ignite helium fusion. Helium fuses to form carbon and oxygen through the triple alpha process, where 3 helium nuclei combine in a delicate nuclear dance. This helium burning phase lasts much shorter than hydrogen burning, perhaps only 100 million years for a Sun-like star. When helium is exhausted, the core contracts again, but for these lower mass stars, it never gets hot enough to ignite carbon fusion. The star's envelope puffs off in a planetary nebula, creating beautiful shells and rings of glowing gas expanding into space at thousands of kilometers per second. The core becomes a white dwarf, a dense stellar remnant about Earth size but containing roughly half the Sun's mass, supported against further collapse by electron degeneracy pressure, a purely quantum mechanical effect. White dwarfs don't generate energy through fusion. They simply cool over trillions of years, radiating away their residual thermal energy like cosmic embers. Eventually, they become black dwarfs, cold stellar corpses at the ambient temperature of the cosmos. However, the universe isn't old enough yet for any white dwarfs to have cooled to this state. Even the oldest white dwarfs, formed perhaps 12 billion years ago, still glow faintly in the darkness. This implosion triggers one of the universe's most violent events, a core collapse supernova. The implosion rebounds as a shockwave that blasts through the star's outer layers, ejecting them into space at velocities of 10,000 to 30,000 kilometers per second. The explosion releases as much energy in a few weeks as the Sun will produce over its entire 10 billion year lifetime. For a brief period, a single supernova can outshine an entire galaxy of 100 billion stars, visible across cosmic distances. The supernova explosion has profound implications for galactic growth and chemical evolution that ripple through space and time. The star's outer layers, enriched with elements synthesized during its life, are scattered through space like cosmic seeds. Carbon and oxygen from helium burning, silicon, sulfur, and calcium from oxygen and silicon burning. And crucially, the supernova explosion itself synthesizes elements heavier than iron through rapid neutron capture called the R process. Gold, platinum, uranium, and other heavy elements form during these violent moments when matter is compressed to unimaginable densities. This enriched material mixes with the interstellar medium, increasing its metallicity. When the next generation of stars forms, they incorporate these heavy elements. Over cosmic time, this process gradually transforms the galaxy's chemical composition. The first stars contained only hydrogen and helium, the primordial elements from the Big Bang. Modern stars contain about 2% heavy elements by mass. This ongoing enrichment is how galaxies grow, not just in mass, but in complexity, in the chemical richness that makes rocky planets and life possible. There's another crucial stellar death mechanism that contributes to chemical enrichment in a different way. When white dwarfs exist in binary systems with companion stars, they can accrete matter from their companions, slowly stealing gas over millions of years. If enough matter accumulates to push the white dwarf above 1.4 solar masses, called the Chandrasekhar limit, electron degeneracy pressure can no longer support the star. The white dwarf collapses, but unlike a core collapse supernova, the entire star undergoes runaway thermonuclear fusion all at once. Carbon and oxygen throughout the white dwarf fuse explosively in what astronomers call a Type Ia supernova. These explosions are remarkably uniform in brightness because they always occur at the same mass threshold, like a cosmic standard candle. This makes them valuable as distance indicators across the universe. More importantly for galactic evolution, they produce copious amounts of iron and nickel, contributing roughly half of all iron in the galaxy, despite being less common than core collapse supernovae. By measuring metallicity in stars of different ages, astronomers can reconstruct the chemical enrichment history like reading tree rings. Old halo stars with ages of 12 billion years have metallicities sometimes 1/100th of solar values or less, barely any heavy elements at all. Thick disk stars 8 to 11 billion years old have metallicities around 1/3 to 1/2 solar. Thin disk stars like the Sun have roughly solar metallicity. The youngest stars forming today have metallicities slightly above solar, continuing the enrichment trend toward a chemically richer universe. The Milky Way spins, a vast pinwheel rotating in the darkness. The Sun completes one orbit every 225 million years at 220 kilometers per second, racing through space at speeds that would cross Earth's diameter in less than a minute. We've only orbited about 20 times since the solar system formed. The last time we were at this position relative to the galactic center, dinosaurs dominated Earth and the supercontinent Pangaea was just beginning to fragment into the continents we know today. But rotation isn't uniform across the galaxy, and that non-uniformity tells us something profound. Near the galactic center, within a few thousand light years, stars orbit in chaotic patterns with high random velocities. This central bulge resembles a swarm of bees rather than organized rotation. Stars zip around on elongated elliptical orbits that carry them thousands of light years from the plane before plunging back through like cosmic yo-yos. The disk where we live shows organized rotation. Stars orbit in roughly circular paths, all moving the same direction like cars on a highway. But there's a critical insight about spiral galaxies that surprises most people and changes how we think about galactic structure. The spiral arms aren't fixed structures rotating rigidly like a pinwheel toy. They're density waves, regions where stars and gas temporarily bunch together, creating the illusion of permanence. Think of it like a traffic jam on a highway. Cars enter from behind, slow down in the congestion, then accelerate out the front. The jam persists in the same location, even though individual cars constantly change. Similarly, stars orbit through spiral arms rather than being permanently part of them. You enter a spiral arm, spend perhaps 50 million years there experiencing higher density and more frequent stellar encounters, then continue your orbit out the other side. The Milky Way probably has 2 major spiral arms plus several minor spurs, though determining structure from inside is challenging. It's like figuring out a building's floor plan while standing in one room with no windows. Radio observations of molecular gas, infrared observations penetrating dust, and optical observations of bright young stars all provide clues about spiral structure, but astronomers still debate whether we have 2, 4, or some intermediate number of major arms. The Sun sits in a minor spur called the Orion Arm or local spur, located between 2 major arms, a relatively quiet neighborhood in galactic terms. To understand where galactic mass comes from, we need to travel back nearly 14 billion years to the universe's first moments. In the beginning, everything was remarkably smooth, almost perfectly uniform. The early universe had nearly uniform density with variations of only 1 part in 100,000. Some regions were slightly denser, others slightly less dense by the tiniest imaginable amounts. These tiny quantum fluctuations from cosmic inflation, that brief period of exponential expansion in the first fraction of a second, created these variations. These tiny differences seem insignificant, barely worth noticing. But give gravity billions of years to work and insignificant becomes dramatic. Microscopic becomes cosmic. Slightly denser regions gravitationally attracted more matter, becoming denser still in a runaway process. Slightly less dense regions lost matter to their denser neighbors, becoming voids. Gravity amplified initial tiny differences through positive feedback over cosmic time, like compound interest building wealth from small initial investments. This process, called gravitational instability, operated on all scales simultaneously from the smallest to the largest. Small clumps formed first within a few 100 million years of the Big Bang. These clumps merged to form larger structures, which merged to form still larger structures, which merged to form galaxies, which merged to form clusters. This hierarchical cascade built all cosmic structure we observe today, from dwarf galaxies to superclusters spanning hundreds of millions of light-years. Dark matter led the way in this cosmic construction project. Because it doesn't interact with radiation, only through gravity, it could collapse freely into clumps while ordinary matter was still coupled to photons, unable to move independently. By the time the universe became transparent at 400,000 years after the Big Bang, dark matter had already begun forming structures, creating gravitational wells. Ordinary matter fell into these dark matter wells over the next few 100 million years, finally free to move and gather. The first stars ignited perhaps 150 to 250 million years after the Big Bang in tiny protogalaxies containing just millions of solar masses. These population 3 stars, never directly observed but predicted by theory and computer simulations, formed from pure hydrogen and helium. No heavy elements existed yet, because no previous stars had lived and died to create them. Meanwhile, those tiny proto-galaxies were merging, colliding, combining. When two passed close together, gravity pulled them into increasingly tight orbits. They lost energy through dynamical friction, where gravitational interactions with surrounding matter act like viscosity in a fluid, and they spiraled together over hundreds of millions of years. The first galaxy mergers occurred perhaps 500 million years after the Big Bang, the beginning of a process that continues today. The Milky Way formed through thousands of these mergers between 12 and 13 billion years ago. Dozens or hundreds of small galaxies containing millions to tens of millions of stars each collided and merged, violently building up the proto-Milky Way's mass. Each merger delivered not just stars but also gas that fueled vigorous star formation. The young Milky Way probably formed stars at 10 to 20 times the current rate during this merger-heavy epoch, blazing brilliantly in the young universe. This violent history left fossils we can still detect today if we know where to look. The stellar halo surrounding the Milky Way contains streams of stars with shared motions and positions, the shredded remains of ancient dwarf galaxies consumed billions of years ago. Chemical analysis reveals diverse element abundances among halo stars, confirming they formed in many separate environments before being violently incorporated into the Milky Way through gravitational conquest. The thick disk, that puffed-up structure containing old stars with random velocities extending 3,000 light-years above and below the plane, also formed during this merger era. Repeated collisions dynamically heated the pre-existing thin disk, increasing stellar velocities and creating the thick disk structure between 8 and 11 billion years ago, a fossil record of violence written in stellar orbits. By about 8 billion years ago, the merger frenzy calmed considerably. The Milky Way had grown large enough that nearby galaxies were significantly smaller by comparison. Major mergers between comparable mass galaxies ceased. The thin disk could then form in relative peace over the last 8 billion years, experiencing only minor disturbances from small satellites rather than catastrophic disruptions from equals. This allowed the organized spiral structure we see today to emerge and persist. But hierarchical merging never stopped completely. It just shifted to smaller scales, becoming more subtle. Every dwarf galaxy currently orbiting the Milky Way represents a future merger waiting to happen. The process that violently assembled the early galaxy continues today, just more gently, because the size difference between the Milky Way and its satellites is now so large. It's the difference between two equal opponents fighting and a giant absorbing tiny objects one by one. In 1994, astronomers Rodrigo Ibata, Mike Irwin, and Jerry Gilmore made a startling discovery that changed everything we thought we knew about galactic cannibalism. They were surveying stars near the galactic center when they noticed something peculiar and unexpected. A group of stars moving differently than they should, not following the Milky Way's organized rotation. Further investigation revealed something shocking. These weren't Milky Way stars at all. They belonged to a small separate galaxy being actively torn apart by our galaxy's tidal forces right now, in real time. This discovery shocked the astronomical community because it proved galactic cannibalism wasn't ancient history locked in the past. It's happening now, close enough to study in exquisite detail. The Sagittarius dwarf elliptical galaxy, as it was named, contains perhaps tens of millions of stars in an elliptical orbit that repeatedly plunges through the Milky Way's disk every few 100 million years. Like a comet orbiting the sun, but made of millions of stars instead of ice. Each passage through the disk is catastrophic for the dwarf galaxy. The Milky Way's gravity pulls harder on the near side than the far side because gravity weakens with distance. This differential force, called a tidal force, stretches the dwarf galaxy along the direction toward the Milky Way while compressing it perpendicular to that direction. Over millions of years and multiple passes, tidal forces literally pull the galaxy apart star by star, dissolving it into space. Astronomers have now mapped the debris streams in exquisite detail using surveys that catalog millions of stars across the sky. The streams wrap completely around the Milky Way multiple times in vast arcs extending hundreds of thousands of light years. Millions of stars that once orbited peacefully in the Sagittarius dwarf now march along these streams, their original galactic identity erased by billions of years of tidal disruption. Eventually, every star will be scattered throughout the Milky Way's halo, indistinguishable from other halo stars, their origin forgotten. But the Sagittarius dwarf is just one victim among many in an ongoing cosmic massacre. As telescopes improved and surveys became more sensitive, astronomers discovered dozens of satellite galaxies orbiting the Milky Way at various distances. Some contain billions of stars like the Magellanic Clouds, visible to the naked eye in the southern hemisphere. Others are ultra-faint dwarfs with just hundreds to thousands of stars spread thinly across hundreds of light years, barely brighter than a single supergiant star. The Canis Major dwarf, discovered in 2003, might be even closer than Sagittarius, perhaps only 25,000 light-years from the galactic center. Its existence remains somewhat controversial because it's so thoroughly disrupted that some astronomers argue it's simply a ripple in the Milky Way's disk rather than a separate galaxy. But chemical analysis of stars in the region suggests they have different compositions than typical disk stars, supporting the interpretation that they originated elsewhere and are being consumed. The Large Magellanic Cloud, Visible as a hazy patch in the southern hemisphere sky, was long considered a peaceful satellite in stable orbit around the Milky Way. Recent measurements changed that picture dramatically and ominously. Data from the European Space Agency's Gaia mission, which has precisely measured positions and velocities for over 1 billion stars, reveals something shocking. The Large Magellanic Cloud isn't in a stable orbit at all. It's falling toward us. Within 2 to 3 billion years, it will collide directly with the Milky Way's disk in a cosmic train wreck. This collision will be spectacular by any measure. The Large Magellanic Cloud contains roughly 20 billion stars. When it plunges through our disk, gravitational interactions will fling stars into new orbits and trigger massive starbursts as gas clouds collide and compress. The impact will disturb the entire galactic disk, creating ripples that propagate outward like waves from a stone dropped in a pond. Eventually, after multiple passes and billions of years of interactions, the Large Magellanic Cloud will be completely absorbed, its stars scattered throughout the Milky Way, adding to our mass. The Small Magellanic Cloud, containing about 7 billion stars, is also doomed to the same fate. The gravitational interaction between the two Magellanic Clouds and the Milky Way creates a complex three-body problem where each object affects the others in unpredictable ways. Current simulations suggest the Small Magellanic Cloud might be captured even sooner than its larger companion, perhaps within 1 to 2 billion years. Together, these two mergers will add roughly 27 billion stars to the Milky Way, increasing our stellar population by perhaps 7% in one dramatic event. Every dwarf galaxy tells a similar story of inevitable doom. The Ursa Major II dwarf, discovered in 2006, is one of the faintest galaxies known, barely distinguishable from a loose star cluster to the untrained eye. Yet chemical analysis confirms its stars formed together in a separate environment before the structure began dissolving into the Milky Way. The Willman I dwarf, found in 2007, may have already been completely disrupted, existing now only as a sparse stream of stars orbiting through the halo, ghosts of a galaxy that once was. New dwarf galaxies continue appearing with nearly every major survey data release. As imaging becomes deeper and computer algorithms better at finding faint structures against the background confusion of Milky Way stars, the satellite population grows. Current estimates suggest 40 to 60 known satellites, but the true population could be hundreds, most too faint to detect with current technology hidden in the darkness. Each satellite represents delivered mass accumulating over cosmic time. Over billions of years, hundreds or thousands of such mergers have built the Milky Way's stellar halo. The halo doesn't form from stars born in place. It's accumulated debris from countless disrupted satellites over cosmic history, a graveyard of cannibalized galaxies, a fossil record written in stellar orbits and chemical compositions. The most transformative recent mission is the European Space Agency's Gaia, launched in 2013. Gaia measures precise positions, parallaxes, and proper motions for over 1 billion stars, about 1% of the Milky Way's total stellar population, but a representative sample. The precision is extraordinary and almost unbelievable. Positions accurate to tens of micro-arcseconds, comparable to measuring a human hair's width from 1,000 kilometers away. Parallaxes, allowing distance measurements to 10% accuracy for stars tens of thousands of light-years away, farther than anyone thought possible from Earth orbit. Gaia's data releases have revolutionized galactic astronomy in ways still being discovered. The second data release in 2018 provided proper motions for over 1 billion stars. Motions across the sky measured with incredible precision. Plotting these revealed substructures throughout the galaxy invisible to previous surveys. Stellar streams appeared as coherent groups of stars with correlated motions. The Gaia-Enceladus merger, an ancient collision between the Milky Way and a massive dwarf galaxy 8 to 11 billion years ago, emerged as a distinct population in velocity space, ghosts from the distant past. The ongoing disruption of the Sagittarius dwarf appeared in exquisite detail with millions of member stars identified. Gaia also measured the approaching motion of the Large Magellanic Cloud, revealing that it's falling toward us faster than previously thought and will collide within 2 to 3 billion years rather than remaining in stable orbit indefinitely. This discovery fundamentally changed our understanding of the Milky Way's near-future evolution, showing the galaxy will undergo major upheavals sooner than expected. And the revolution isn't over. New tools are still unlocking the galaxy's secrets. Stars don't form from nothing, materializing out of empty space. They form from gas clouds that collapse under gravity's relentless pull. This presents a fundamental puzzle that should trouble anyone who thinks about it carefully. The Milky Way has been forming stars for nearly 13 billion years at varying but always substantial rates. Simple arithmetic says this should have exhausted the gas supply billions of years ago, leaving a dead galaxy of slowly fading stars and cold remnants. Yet star formation continues today across the galaxy. Molecular clouds throughout the disk are actively collapsing to form new stellar systems right now. The Orion Nebula, 1,300 light-years away, contains over 3,000 young stars less than a few million years old, still forming from surrounding gas that glows beautifully in telescopic images. The Carina Nebula harbors some of the most massive stars known, hundreds of times more luminous than the Sun, born within the last few million years in violent stellar nurseries. The Eagle Nebula's iconic pillars of creation, photographed by Hubble and now by Webb, show finger-like protrusions of dense gas where new stars are gestating, protected from destructive radiation by surrounding dust. Where does all this gas come from? The Milky Way must be continuously replenished from external sources, a steady rain of new material. Understanding this gas supply is crucial for understanding galactic growth, because gas eventually becomes stars through gravitational collapse. Tracking gas inflow helps us understand not just present star formation, but future growth for billions of years to come, the galaxy's destiny. In the galaxy's youth, billions of years ago, gas accretion was straightforward and efficient. The universe was denser and hotter, filled with pristine hydrogen and helium. Cold gas flowed along filaments of the cosmic web, those vast threads of matter connecting galaxies across hundreds of millions of light-years. This cold-mode accretion delivered gas directly to galactic disks where it could immediately form stars. The gas never heated up significantly because it flowed along specific paths determined by the cosmic web's geometry, channeled like water through streams. Think of the cosmic web as a highway system with galaxies sitting at intersections where multiple highways meet. Gas flows along these highways like traffic, collected by galaxies sitting at the crossroads. In the early universe, this traffic was heavy and fast, a cosmic rush hour. Young galaxies at high redshift, which we observe billions of light-years away, as they existed billions of years ago. show evidence of vigorous cold gas accretion feeding star formation rates 10 to 100 times higher than typical local galaxies. But as galaxies grew more massive over cosmic time, physics changed dramatically. Larger galaxies have deeper gravitational potential wells, stronger gravity. Gas falling into these wells accelerates to higher velocities before arriving, gaining tremendous kinetic energy. When fast-moving, gas collides with material already orbiting the galaxy, shocks form inevitably. These shocks convert kinetic energy into thermal energy through compression, heating the gas to millions of degrees, far too hot for star formation. This creates what astronomers call hot mode accretion, a completely different regime. Instead of flowing directly into the disk, gas gets shock-heated and forms a massive corona or hot halo surrounding the galaxy like an invisible atmosphere. This hot gas is in approximate hydrostatic equilibrium, where outward thermal pressure balances inward gravitational pull. It doesn't immediately fall into the disk. Instead, it slowly cools through radiation over hundreds of millions or billions of years, a cosmic waiting period. As hot gas cools, it becomes denser and begins sinking toward the disk under gravity's pull. Eventually, perhaps after a billion years or more of gradual cooling, cooled gas reaches the disk and can finally participate in star formation. This cooling process provides a steady trickle of gas, sustaining ongoing star formation at moderate rates rather than the intense bursts characteristic of cold mode accretion. It's like the difference between a flash flood and a gentle rain that continues for years. The Milky Way transitioned from cold to hot mode accretion roughly 8 to 10 billion years ago when it reached a critical mass threshold around 30 to 50 billion solar masses. Before that transition, star formation rates were much higher, perhaps 10 to 20 solar masses per year, blazing brilliantly. After the transition, rates declined to 1 to 3 solar masses per year, where they've remained roughly stable for billions of years, a more sustainable pace. This hot halo remains invisible to most observations because the gas is so diffuse and hot, spread across enormous volumes. The best detections come from X-ray telescopes that can observe emission from million-degree gas glowing in X-rays. These observations suggest the hot halo contains enormous mass, potentially 50 to 100 billion solar masses of gas, more mass than all the stars in the galaxy combined. If correct, the Milky Way has enough material in its halo to sustain star formation for another 10 to 20 billion years, long after the Sun dies and Earth becomes uninhabitable, long into the distant future. But there's another gas source more directly observable to radio telescopes. High-velocity clouds, regions of neutral hydrogen floating above and below the galactic disk, were discovered in the 1960s and puzzled astronomers. They're called high velocity because their velocities don't match organized disk rotation, suggesting they're falling toward or being ejected from the disk, material in motion. Some high-velocity clouds are fountain flow, gas blown out of the disk by supernova explosions and stellar winds that rises into the halo, cools, and falls back down in an endless cycle. Massive stars inject enormous energy into the interstellar medium through powerful stellar winds and explosive deaths. This energy can accelerate gas to escape velocities, launching it thousands of light-years above the disk. Once in the halo, the gas cools through radiation and gravity, pulls it back down in a cosmic fountain cycle, recycling material between disk and halo. Other high-velocity clouds appear pristine, containing very low abundances of heavy elements, barely enriched beyond primordial composition. These clouds likely represent genuine accretion, gas falling into the Milky Way for the first time from the intergalactic medium. They've never been part of any galaxy, never processed through stars, remaining largely unchanged since shortly after the Big Bang. When this primitive gas falls into the disk, it dilutes the enriched material already there, temporarily reducing average metallicity before star formation enriches it again. The Magellanic Stream represents the most spectacular example of ongoing gas accretion visible in radio telescopes. This vast arc of neutral hydrogen, discovered in the 1970s through radio observations, stretches over 150 degrees across the southern sky. That's roughly the angle from horizon straight up to overhead, and then 3/4 of the way back down to the opposite horizon, an enormous structure. The stream contains hundreds of millions of solar masses of hydrogen stripped from the Magellanic Clouds by tidal forces and ram pressure, material torn away and left behind. Ram pressure occurs when the Magellanic Clouds move through the Milky Way's diffuse halo gas. Even though this halo gas is incredibly tenuous by terrestrial standards, thinner than any vacuum we can create on Earth, the Magellanic Clouds are moving at several hundred kilometers per second through it. At those velocities, even tenuous gas creates a wind that blows back on the clouds like air resistance affects a fast-moving car. This wind strips gas from the cloud's outer regions, leaving it trailing behind in vast streams, marking their path through space. Over the next few 100 million years, different parts of the Magellanic Stream will fall into the Milky Way's disk at different locations scattered around the galaxy. Each impact will compress disk gas, triggering bursts of star formation. The total mass is sufficient to form hundreds of millions of new stars, potentially increasing the star formation rate temporarily by factors of several, a gift from our satellite galaxies. At the very heart of the Milky Way sits a monster, invisible but undeniable. Sagittarius A star, the central supermassive black hole, contains 4.15 million solar masses compressed into a region no larger than Mercury's orbit around the Sun, an almost incomprehensible density. We can't see it directly because black holes emit no light by definition. But we can observe stars orbiting around it, and their motions reveal the invisible mass at the center with mathematical certainty. The closest star observed, designated S2, follows an elliptical 16-year orbit around the invisible center. At closest approach, called periapsis, S2 comes within 17 light hours of the event horizon, just 17 times farther than Pluto orbits from the Sun. At that point, the star reaches nearly 2% of light speed, about 5,000 kilometers per second, velocities that test the limits of general relativity. These extreme velocities occur because Sagittarius A star's gravity is so intense, warping space-time dramatically. By tracking S2 and dozens of other stars for over 2 decades, astronomers can apply Kepler's laws combined with general relativistic corrections to measure the central mass with extraordinary precision. The observations leave no doubt whatsoever. 4.15 million solar masses concentrated in a tiny region. Only a black hole can pack that much mass into such small volume without emitting detectable light, without revealing itself directly. But here's what surprises many people about our galaxy's central black hole. Sagittarius A star is remarkably quiet, almost dormant. It currently accretes matter at very low rates, perhaps 1/100th of 1% of a solar mass per year. That's roughly the mass of Earth every 300 years, barely a meal by black hole standards. At this rate, the black hole would take hundreds of billions of years to double its mass through accretion alone, longer than the current age of the universe. This quiescence seems puzzling at first glance. The galactic center region contains substantial amounts of gas and stars. Molecular clouds with masses of millions of suns orbit within just a few light years of the black hole, tantalizingly close. Yet very little material actually falls in, most remains in orbit. The reason appears to be angular momentum, the tendency of rotating objects to resist change. Gas in the galactic center has significant angular momentum from the galaxy's rotation. For this gas to fall into the black hole, it must somehow shed most of its angular momentum, a difficult process. In other galaxies with actively feeding black holes, this happens efficiently through turbulence in dense accretion disks where friction and magnetic fields transport angular momentum outward. But around Sagittarius A star, the gas is too hot and diffused to form a dense disk. It exists as a low-density hot accretion flow where viscosity is low and angular momentum transport inefficient. Most gas simply orbits without falling in, circling endlessly. This hasn't always been the case, and the evidence is written in light. Molecular clouds near the galactic center show bright X-ray emission on their surfaces that can only be explained as reflection of much more intense radiation from the central source in the past. The spectrum of this reflected emission matches hot gas near a black hole, not any other source. The light travel time from Sagittarius A star to these clouds is several hundred years, meaning we're seeing delayed reflection of an outburst that occurred roughly 300 to 400 years ago, an echo from the past. How bright was this outburst? Based on reflection intensity and cloud geometry, Sagittarius A star must have been at least 1 million times more luminous than today, possibly much more, briefly blazing across the galaxy. For some period, perhaps years to decades, our galaxy's central black hole was actively feeding on something substantial. What triggered this remains uncertain. Perhaps a gas cloud fell in. Perhaps a star wandered too close and was tidally ripped apart, its remains feeding the black hole in a cosmic feast. Whatever the cause, it proves Sagittarius A star is capable of far more dramatic activity than its current state suggests, a sleeping giant that occasionally awakens. Looking forward into the distant future, the biggest event in Sagittarius A star's lifetime occurs in approximately 4 billion years when it merges with Andromeda's central black hole. That black hole contains roughly 100 to 200 million solar masses, about 40 times more massive than Sagittarius A star, a much larger monster. The merger will produce gravitational waves detectable across the observable universe and likely trigger brilliant quasar emission visible for millions of years, one of the most spectacular events possible in the cosmos. Andromeda is coming. The nearest large galaxy to us, about 2.5 million light-years away, is approaching at 110 kilometers per second, closing the distance relentlessly. For decades, astronomers knew this from spectroscopy. Andromeda's light shows a blue shift, meaning it's moving toward us rather than receding like most galaxies in the expanding universe, a nearby exception to cosmic expansion. But approach velocity alone doesn't guarantee collision. Imagine throwing a ball past someone standing 10 feet away. If you throw it fast enough sideways, it will miss even though it's moving in their general direction. Similarly, Andromeda might pass by at an angle rather than hitting directly. Determining whether collision will occur required measuring Andromeda's transverse motion, its sideways motion across the sky perpendicular to our line of sight. This measurement is extraordinarily difficult, one of the hardest in astronomy. Even for a galaxy moving hundreds of kilometers per second, the angular motion across the sky is minuscule due to the vast distance involved. From Earth's perspective, Andromeda moves across the sky by just one moon diameter every 15,000 years, barely perceptible. Measuring this required the Hubble Space Telescope tracking individual stars in Andromeda over multiple years to detect tiny positional shifts measured in milliarc seconds. In 2012, the answer came after years of painstaking observations. Andromeda's transverse velocity is small, much less than its approach velocity. The galaxy is heading almost directly toward us, like an arrow aimed at a target. Collision is inevitable barring some unknown intervention, occurring in approximately 4 billion years, give or take a few hundred million years, depending on exact masses and dark matter distributions. What happens during this collision will transform both galaxies beyond recognition into something neither resembles. The first close passage will occur when Andromeda and the Milky Way are separated by perhaps 500,000 light-years, about twice the current distance between the Milky Way and the Magellanic Clouds. At that point, tidal forces become significant and destructive. Each galaxy raises tides on the other, pulling stars outward into vast tidal tails extending hundreds of thousands of light-years into intergalactic space like cosmic tentacles. Computer simulations show these tidal tails can contain billions of stars flung from their parent galaxies by gravitational interactions, cast out into the void. Some will eventually fall back and be reincorporated during later passages. Others will be permanently ejected, destined to wander intergalactic space alone for the rest of cosmic time. For those stars and any planets orbiting them, the sky will transform over millions of years as their galactic home recedes into the distance, eventually becoming just one more faint fuzzy patch among many, an orphaned system adrift. The first close passage won't result in immediate merger despite the violence. Like two balls colliding at an angle, the galaxies will pass through each other and separate again, each moving away on the momentum of their approach. But gravitational interactions during the passage will have removed orbital energy through tidal friction and gravitational drag. Neither will have escape velocity. They'll fall back together for a second passage, inexorably drawn by gravity. The second passage will be more disruptive than the first. The galaxies will penetrate deeper into each other's gravitational wells, creating stronger tides and flinging more stars into intergalactic space. Gas clouds will collide violently because, unlike stars, gas can't pass through itself without interacting. When giant molecular clouds moving at hundreds of kilometers per second collide head-on, they shock heat and compress dramatically, triggering massive starbursts, periods of intense star formation far exceeding normal rates. By the third or fourth passage, perhaps 2 to 3 billion years after first encounter, the galaxies will have lost so much orbital energy through repeated interactions that they can no longer separate. They'll merge into a single chaotic irregular structure filled with stars on highly elongated orbits, a cosmic mess. This irregular galaxy will then gradually relax over the next few billion years through what astronomers call violent relaxation, where gravitational interactions redistribute energy and circularize orbits, slowly creating order from chaos. The final product, informally called Milky Way or Milkdromeda by astronomers, will be a giant elliptical galaxy containing over 1 trillion stars, roughly double the current population of both galaxies combined. It will no longer show spiral structure, but rather a smooth ellipsoidal distribution of stars like a cosmic football. Most gas will have been consumed in the merger starburst or ejected by stellar winds and supernovae. Star formation will largely cease except for occasional bursts when small amounts of residual gas manage to cool and collapse, a dying galaxy slowly fading. The central region will host a single supermassive black hole containing roughly 200 million solar masses, formed when Sagittarius A star and Andromeda's central black hole merge after spiraling together through dynamical friction over millions of years. This merger itself will produce gravitational waves, ripples in space-time detectable by future space-based observatories like LISA, one of the most energetic events in the universe. What happens to Earth during all this cosmic chaos? The answer contains significant uncertainty because stellar trajectories during mergers have large random components, unpredictable elements. Simulations provide only statistical predictions, probabilities rather than certainties. There's roughly a 50% chance the solar system ends up in the outer regions of Milkomeda, 2 to 3 times farther from the center than now, flung outward by gravitational interactions. About 40% probability of ending up at similar distances with different orbital orientations, shuffled but not displaced. And roughly 10% chance of dramatic outcomes like ejection into intergalactic space or being flung into the central regions near the supermassive black hole, extreme fates. But these outcomes are academic, because Earth will already be dead by then. 4 billion years from now, the Sun will be near the end of its main sequence lifetime, having steadily brightened as helium accumulates in its core and changes its internal structure. By that time, the Sun will be about 40% more luminous than today, blazing brilliantly. This increased luminosity will have boiled away Earth's oceans, stripped the atmosphere through intense ultraviolet radiation, and rendered our planet a scorched, lifeless rock long before the galaxy collision occurs. Earth's habitability ends roughly 1 billion years from now, long before the cosmic merger. For the galaxy itself, the merger represents a transformation from youth to old age, from vigorous activity to quiescent retirement. Spiral galaxies like the Milky Way and Andromeda are young and active in galactic terms, still forming stars and evolving chemically, still alive and growing. Elliptical galaxies like Milky Way will become are old and passive, their star formation finished, their evolution essentially over. They coast through cosmic time, slowly fading as their stars age and die without new generations to replace them, monuments to a more active past. To truly understand how galaxies grow through cannibalism, we need to understand the physics of tidal forces and how they tear structures apart. This applies not just to dwarf galaxies being consumed by the Milky Way, but to any object venturing into strong gravitational fields, from comets approaching the Sun to stars approaching black holes to galaxies approaching each other. Tidal forces arise because gravity weakens with distance, a simple geometric fact with profound consequences. Consider a dwarf galaxy orbiting the Milky Way. The side of the dwarf facing toward the Milky Way experiences stronger gravitational pull than the side facing away because it's closer to the source of gravity. This differential force stretches the dwarf along the direction toward the Milky Way, while compressing it perpendicular to that direction, distorting its shape. The mathematics is straightforward, but the implications are profound and far-reaching. The tidal force is proportional to the mass of the larger object, the size of the smaller object, and inversely proportional to the cube of the distance. That cubic dependence means tidal forces increase extremely rapidly as objects get closer, explosively so. Double the distance, and tidal forces decrease by a factor of 8. Halve the distance, and they increase 8-fold, a dramatic change. For a dwarf galaxy orbiting the Milky Way, we can calculate when tidal forces become strong enough to disrupt it completely. This occurs when the tidal force across the dwarf exceeds the dwarf's own self-gravity, holding it together, overwhelming internal cohesion. The critical distance depends on both galaxies' masses and the dwarf's internal density distribution. A more massive Milky Way creates stronger tides, more destructive forces. A more diffuse dwarf galaxy has weaker self-gravity and disrupts more easily, succumbing quickly. A denser compact dwarf resists disruption better, surviving longer. The disruption process unfolds over multiple orbits, a slow death across cosmic time. On the first close passage, tidal forces strip stars and gas from the dwarf's outer regions where self-gravity is weakest and resistance minimal. This material doesn't immediately disperse into space. It remains concentrated near the dwarf, forming a tidal tail trailing behind and extending ahead along the orbit. The dwarf has essentially been stretched along its orbital path like taffy being pulled. As the dwarf recedes from periapsis, the closest approach point, tidal forces weaken and stripping temporarily ceases. But the damage is done and permanent. The dwarf has lost mass, reducing its self-gravity for future encounters. And the stripped material in tidal tails will eventually spread out along the entire orbit, forming a stream marking the dwarf's path through space. On the next orbital passage, tidal forces strip deeper layers because the dwarf's reduced mass means weaker self-gravity holding remaining material together. More material joins the tidal tails and streams, feeding the growing tendrils. After multiple passages spanning hundreds of millions to billions of years depending on orbital period, the dwarf is completely disrupted. All its stars and gas have been stripped and scattered into streams wrapping around the larger galaxy multiple times, a cosmic dissolution. The Sagittarius dwarf provides the best-studied example of this process unfolding in real time. Its orbital period is roughly 1 billion years, completing one revolution in that time. Each passage through the Milky Way's disk, occurring every several 100 million years, strips significant mass in violent tidal encounters. The streams have been mapped wrapping around the Milky Way multiple times, leading and trailing the dwarf's current position like ribbons. Computer simulations can reproduce these streams remarkably well, confirming our theoretical understanding of tidal disruption is fundamentally correct. But tidal disruption isn't instantaneous or uniform, a simple process. Different parts of the dwarf respond differently depending on their positions and velocities within the dwarf's internal structure. Stars near the dwarf's center, deep within its gravitational potential well, are stripped last, holding on longest. Stars in the outer regions are stripped first, lost quickly. This creates an age gradient in the streams where stars stripped earlier are more widely dispersed, while recently stripped stars remain concentrated near the current dwarf position, a timeline written in stellar positions. Chemical abundances also show patterns revealing the dwarf's history. If the dwarf experienced multiple epochs of star formation with different metallicities at different times, stars of different ages will have different chemical compositions. The streams preserve this information, allowing astronomers to reconstruct the dwarf's star formation history by analyzing chemical abundances in stream stars at different positions. Each star carries a message about when and where it formed. The mathematics of tidal disruption also explains the Roche limit, the distance within which tidal forces exceed self-gravity for any gravitationally bound object, a fundamental boundary. For a fluid body with no tensile strength, like a water droplet or gas cloud, the Roche limit is about 2.4 times the larger object's radius, multiplied by the ratio of densities to the 1/3 power. For solid bodies with tensile strength, the limit is closer at roughly 2.4 times the radius, though exact values depend on material properties. This explains phenomena throughout astronomy at every scale. Saturn's rings lie within Saturn's Roche limit, meaning any moon trying to form there would be tidally disrupted before gravity could assemble it, torn apart as fast as it formed. Comet Shoemaker-Levy 9 was torn apart by tidal forces when it passed within Jupiter's Roche limit in 1992, fragmenting into over 20 pieces that subsequently impacted Jupiter in 1994 in a spectacular display. Stars can be tidally disrupted if they pass too close to supermassive black holes, producing spectacular flares called tidal disruption events visible across cosmological distances. For galaxies, the concept is similar but more complex, because galaxies aren't solid bodies or simple fluids. They're self-gravitating systems where each star orbits independently in the galaxy's collective gravitational field, a fluid of stars. The Roche limit for a dwarf galaxy isn't a single well-defined radius, but rather depends on the dwarf's internal structure, density profile, and orbital eccentricity, a more nuanced boundary. Orbital eccentricity matters tremendously because highly elliptical orbits have much closer periapsis passages than circular orbits with the same average distance. The Sagittarius dwarf has an elliptical orbit that brings it within about 50,000 light-years of the Milky Way's center at periapsis, while taking it beyond 200,000 light-years at apoapsis, a dramatic range. The strong tidal forces during periapsis passages do most of the damage in brief violent encounters, while the dwarf experiences relatively gentle conditions at apoapsis where it can partially recover. This explains why some satellites survive longer than others despite similar masses. Satellites on circular orbits at large distances experience moderate but constant tidal forces and can survive billions of years, aging slowly. Satellites on highly elliptical orbits experience extreme tidal forces during periapsis that quickly strip them in just a few passages. And satellites on radial orbits that plunge nearly straight toward the galactic center might be destroyed in a single dramatic passage, torn apart in one violent encounter. Dark matter plays a crucial but complicated role in all of this. Dwarf galaxies are dominated by dark matter, with dark matter outweighing visible matter by factors of 10 to 100 or more, providing most of the gravitational binding. This dark matter provides additional self-gravity that helps resist tidal disruption. A dwarf galaxy with substantial dark matter can survive stronger tidal forces than a similar stellar mass without dark matter, protected by invisible mass. But dark matter also complicates observations frustratingly. We can only see the stars and gas being stripped, the visible matter. The dark matter, being invisible by definition, could be stripped at different rates depending on its distribution. If the dark matter is more extended than the visible matter, it might be stripped preferentially, leaving a more compact, visible remnant. If the dark matter is concentrated, it might resist disruption even after visible matter is stripped, an invisible core remaining. Observations of stellar streams can constrain dark matter distributions through detailed analysis of stream properties. The width, density profile, and velocity dispersion of streams depend on the parent dwarf's mass distribution, including dark matter halos. By comparing observations to simulations with different dark matter profiles, astronomers can infer properties of the dark matter that would be difficult or impossible to measure directly in the intact dwarf galaxy. Tidal disruption also generates tidal heating, increasing random velocities of stars within the dwarf through gravitational work. When tidal forces stretch and compress the galaxy repeatedly, stars at different positions experience different forces. These differential forces do work on the stars, increasing their kinetic energies through gravitational pumping. Over multiple orbits, this tidal heating puffs up the dwarf structure, making it more diffuse and, ironically, more vulnerable to further tidal stripping in a self-reinforcing process. The streams themselves are dynamically cold initially, meaning stars within them have very similar velocities, moving together. This occurs because tidal stripping removes stars gently, preserving their orbital velocities. Stars in streams move nearly in lockstep like beads on a string, marching together through space. But over time, measured in billions of years, differential gravitational forces from the Milky Way's non-spherical mass distribution spread the streams, increasing velocity dispersions. Eventually, after billions of years, streams dissolve completely into the smooth stellar halo, their identity erased. This life cycle from bound dwarf galaxy to coherent stream to dissolved halo component explains the stellar halo's structure and composition. The halo contains both relatively young streams from ongoing disruptions like Sagittarius and ancient dissolved streams from disruptions billions of years ago, a mixture of ages. By studying the halo's phase space distribution, the positions and velocities of halo stars, astronomers can decompose it into components from different ancient merger events, reading the fossil record of galactic cannibalism written in the orbits of stars. The Milky Way-Andromeda merger won't be the final transformation in our corner of the universe. The local group, that collection of over 50 galaxies, including the Milky Way, Andromeda, and dozens of dwarfs, will continue evolving long after the main merger completes. The Triangulum Galaxy, M33, contains roughly 40 billion stars and is currently bound to Andromeda at about 250,000 light-years distance. It will likely merge with Milkomeda within several billion years of the main merger, adding its mass to the growing structure in yet another cosmic collision. Other local group members face similar fates of inevitable absorption. The dwarf galaxies scattered throughout the volume, currently orbiting either the Milky Way or Andromeda in their gravitational domains, will gradually fall into Milkomeda over timescales of 10 to 100 billion years. Each merger adds mass, though dwarf contributions are small compared to the major mergers already discussed, incremental additions to an already massive galaxy. Beyond the local group, the nearest significant structure is the Virgo cluster, about 55 million light-years away. Virgo contains thousands of galaxies anchored by several massive ellipticals at its core. It's the gravitational center for our region of the universe, the dominant mass concentration. The local group and many nearby galaxy groups are slowly falling toward Virgo, accelerating inward at roughly 300 kilometers per second, drawn by its immense gravity. Will we eventually merge with Virgo in the distant future? This depends on dark energy's influence, that mysterious force driving cosmic acceleration. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating rather than decelerating, opposite what gravity alone would predict. This acceleration requires a new component called dark energy, which makes up roughly 70% of the universe's total energy density. Dark energy acts opposite to gravity, not pulling things together, but pushing them apart, causing space itself to expand at an accelerating rate. Structures already gravitationally bound will continue merging despite dark energy's push. The local group is bound and will complete its mergers over the next tens of billions of years. Dark energy unable to tear apart what gravity has already joined. But more distant structures that aren't yet bound will be pushed apart faster than they can fall together, driven away by accelerating expansion. The critical question is whether the local group and Virgo are truly gravitationally bound or simply falling toward each other within an overall expansion that will eventually tear them apart before they can merge. Current estimates suggest they're not quite bound, falling just short of the threshold. Dark energy is winning the cosmic tug-of-war. The local group will merge into Milky Way and absorb a few nearby small groups caught in its gravitational grasp. But Virgo will recede beyond reach, pushed away by accelerating expansion. Within approximately 200 billion years, accelerating expansion will push all galaxies outside our local group beyond the cosmic horizon, the distance beyond which light can no longer reach us due to space expanding faster than light can cross it, an ultimate isolation. At that point in the unimaginably distant future, Milky Way becomes an island universe alone in an exponentially expanding cosmos. Any astronomers living then and looking out will see empty space in every direction, nothing but darkness. No distant galaxies, no quasars, no large-scale structure visible. Just their merged local group surrounded by darkness expanding forever. They'll have no direct evidence that other galaxies exist unless they discover ancient records or theorize backward from cosmic microwave background observations, if those are even still detectable. This isolation means growth will effectively end for Milky Way. All nearby dwarfs will have been consumed, absorbed into the growing mass. All major mergers completed. The only remaining growth will be slow star formation from residual gas, and even that will cease within perhaps 100 billion years after the last gas is exhausted or ejected. At that point, Milky Way will contain roughly 1.5 to 2 trillion stars, nearly all its future growth already finished, a final stable configuration. After star formation ceases, Milky Way enters a long decline lasting trillions of years, an entropic fade. The massive stars, those 10 times more massive than the Sun, will have already died long ago, having lived just a few million to tens of millions of years before exploding as supernovae. Sun-like stars will exhaust their hydrogen fuel and swell into red giants before shedding their outer layers and becoming white dwarfs, dead stellar cores supported against collapse by quantum electron degeneracy pressure, slowly cooling remnants. Low-mass red dwarfs, the most common stars in the universe, will continue shining for trillions of years, the last lights burning. A red dwarf with 10% of the Sun's mass will burn for 10 trillion years, about 700 times longer than the current age of the universe, an almost unimaginable duration. These dim stars will be the last lights in the galaxy, slowly fusing hydrogen into helium at a pace so leisurely that their fuel supply lasts nearly forever by human standards of time. But eventually, inevitably, even red dwarfs exhaust their fuel. The last one will die perhaps 10 to 15 trillion years from now, leaving behind a white dwarf that cools over subsequent trillions of years, fading into darkness. By then, Milky Way will be a graveyard of stellar remnants. White dwarfs, neutron stars from ancient supernova explosions, stellar mass black holes, and brown dwarfs that never ignited fusion will orbit silently in the darkness, cold and dead, monuments to a more active past. Even this remnant population won't last forever in the ultra-long term. Gravitational interactions between orbiting objects lead to energy exchange through close encounters. Close encounters can give one object enough energy to reach escape velocity, flinging it into intergalactic space, while the other loses energy and sinks deeper into the gravitational well, a cosmic redistribution. This process, called evaporation, slowly disperses the galaxy over timescales of 10 to the power of 20 years, roughly 10 billion trillion times the current age of the universe, an incomprehensible duration. Computer simulations show that after this evaporation phase, perhaps 1 to 10% of the galaxy's mass remains in a dense core of tightly bound remnants surrounding the central black hole. The rest has been ejected into intergalactic space, doomed to wander alone through an exponentially expanding cosmos, where the space between objects doubles every 10 billion years or so, eternal exile. Those remnants that remain will gradually spiral inward toward the central black hole. Binary systems lose energy through gravitational wave emission, ripples in spacetime carrying energy away, causing orbits to decay over trillions of years. Eventually, they either merge or fall into the central black hole, feeding it one last time. Over timescales approaching 10 to the power of 30 years, most remaining mass either merges with the central black hole or collides with other remnants and produces gravitational wave bursts before falling in. Final meals for the cosmic monster. The central black hole grows slowly through these final meals, perhaps doubling or tripling its mass from 200 million to 400 or 600 million solar masses over incomprehensible timescales. Then, even this black hole, the last massive object remaining, begins evaporating through a quantum mechanical process. In 1974, Stephen Hawking made a revolutionary discovery combining quantum mechanics with general relativity that changed everything. Black holes aren't completely black. They emit thermal radiation through quantum effects near the event horizon, a purely quantum phenomenon. Virtual particle pairs constantly pop into existence everywhere in space due to quantum fluctuations appearing and disappearing. Near a black hole's event horizon, the intense tidal forces can separate these pairs before they annihilate. One particle falls in while the other escapes, carrying away energy that ultimately comes from the black hole's mass, slowly draining it. To an external observer, the black hole appears to radiate with a temperature inversely proportional to its mass, colder for larger black holes. Larger black holes have lower temperatures. For a black hole the mass of the Sun, the Hawking temperature is about 1/10,000,000th of a degree above absolute zero, incredibly cold. For Milky Way's central black hole containing roughly 600 million solar masses after final accretion, the temperature is about 6 billionths of a degree, almost at absolute zero. This is far colder than the cosmic microwave background, which currently sits at 2.7 degrees Kelvin. So currently, the black hole is actually absorbing more energy from background radiation than it emits through Hawking radiation. It's growing, not shrinking, though at a negligible rate of perhaps a few atoms per second, barely perceptible. But the universe is expanding and cooling relentlessly. The background temperature decreases inversely with the universe's scale factor. As the universe doubles in size, the temperature drops by half. Eventually, perhaps 10 to the power of 20 years in the future, when the universe is 1 billion times older than today, the background temperature will cool below the black hole's Hawking temperature. At that point, the black hole begins losing mass through evaporation faster than it gains through absorption, finally beginning to shrink. The evaporation timescale is proportional to the cube of the black hole's mass, growing rapidly with size. For a 600 million solar mass black hole, complete evaporation takes roughly 2 × 10 to the power of 98 years. That's a 2 followed by 98 zeros, a number with no meaningful comparison in human experience. It's roughly 10 to the power of 88 times longer than the current age of the universe, unimaginably vast. As the black hole shrinks, its temperature increases, causing it to radiate faster and shrink even more rapidly in a runaway process, accelerating toward oblivion. When the black hole reaches roughly the mass of a large mountain, about 10 to the power of 15 kilograms, it radiates with stellar luminosity, blazing briefly. In its final microseconds, it radiates with the power of billions of suns concentrated in a tiny region. The final moments produce a burst of high-energy particles and radiation, as the last remnants of mass energy convert according to Einstein's E = mc², a flash and then nothing. Then, Milky Way's last vestige disappears completely. Its immense mass has been scattered across an exponentially expanding universe as faint radiation gradually thermalizing with the background, dissipating completely. This is the heat death, maximum entropy, complete thermal equilibrium, the ultimate fate. No energy gradients exist to power any processes. No stars shine. No black holes lurk. Only an ultra-cold bath of ultra-dilute radiation approaches absolute zero across ever-expanding space, eternal stillness. Let's step back from cosmic far-future scenarios and return to something more immediate and personal, more relevant to our existence. The Milky Way's growth over billions of years didn't just add mass to a number on a page. It created the chemical complexity necessary for life, for planets, for consciousness itself. Understanding this chemical evolution helps us understand our own origins and place in the cosmos, our connection to the stars. When the universe was 5 minutes old in its earliest moments, primordial nucleosynthesis produced hydrogen, helium, and traces of lithium. Nothing heavier than that. The first stars that formed perhaps 200 million years after the Big Bang contained only these three elements. No carbon, no oxygen, no nitrogen, no iron, none of the elements essential for rocky planets or biological chemistry, none of the building blocks of life. These first-generation stars, called population 3 stars, were probably extremely massive, perhaps 100 to 300 solar masses, giants by modern standards. At those masses, they burned through nuclear fuel in just a few million years before exploding as pair instability supernovae, completely disrupting without leaving remnants, total annihilation. These explosions synthesized and scattered the first heavy elements into surrounding space like cosmic seeds. Carbon and oxygen formed in helium-burning shells during the star's final days. Silicon and iron synthesized during the supernova explosion itself as the shockwave plowed through stellar layers at incredible speeds. These elements mixed with pristine hydrogen and helium, creating the first chemically enriched gas from which the next generation of stars would form, slightly richer. Generation by generation, stellar nucleosynthesis increased heavy element abundances. Each generation of massive stars lived fast, died young, and enriched the interstellar medium with their remains. Each generation formed planets with slightly higher abundances of heavy elements, more complex chemistry. This process, called chemical evolution, gradually transformed the universe from pure hydrogen and helium to the chemically complex cosmos we inhabit today, enabling everything we see. The Sun formed 4.6 billion years ago from an interstellar cloud enriched by roughly 9 billion years of previous stellar generations, countless stars that lived and died before us. That cloud contained about 1.8% heavy elements by mass. This was enough to form rocky planets like Earth, providing the raw materials. Enough to provide the raw materials for biological molecules, the chemistry of life. Enough to create the complex chemistry supporting life itself. Every atom in your body except hydrogen was synthesized in a star or supernova billions of years ago. The calcium in your bones formed in massive stars that exploded as supernovae billions of years ago, scattered across light years of space. The iron in your blood was created during supernova explosions and scattered through space by shock waves. The carbon, nitrogen, and oxygen making up most of your mass were forged through stellar nucleosynthesis and distributed when those stars died, returned to the cosmos. This is why the Milky Way's growth matters on a deeply personal level that transcends astronomy. Without billions of years of stellar births and deaths, without generations of stars enriching the interstellar medium, without the chemical evolution that accompanied galactic growth, we wouldn't exist. The atoms comprising our bodies, the elements supporting chemistry complex enough for life and consciousness, all of it required the Milky Way's long history of growth and transformation. We are products of galactic evolution. When we say the Milky Way is growing, we're describing the ongoing process that made our existence possible. The galaxy continues adding mass through star formation and mergers. Each new star that forms will eventually die, perhaps in a supernova that scatters newly synthesized elements through space, continuing the cycle. Those elements will be incorporated into the next generation of stars and planets, perpetuating creation. The cycle continues, slowly increasing chemical complexity throughout cosmic history, building toward ever greater richness. Let's quantify exactly what growing every second means in concrete terms that we can grasp. These numbers help ground abstract concepts in measurable reality, making the invisible visible. Star formation occurs at roughly 1.5 solar masses per year, averaged across the entire Milky Way, integrated over all regions. That's about 2.8 times 10 to the power of 27 kilograms per year. Divided by seconds in a year, roughly 31 million, this gives roughly 9 times 10 to the power of 19 kilograms per second. That's 90 billion trillion kilograms every second, converting from diffuse gas into dense protostellar cores, matter transforming. For comparison, Earth's mass is roughly 6 times 10 to the power of 24 kilograms. So every week, the Milky Way forms roughly 1 Earth mass worth of new stars, an entire planet's worth of matter compressed into stellar furnaces. Every year, about 50 Earth masses, over 1 million years, about 50 million Earth masses, or roughly 1/8 the mass of Jupiter, substantial accumulation. When we say the Milky Way is growing, we're describing the ongoing process that made our existence possible. The galaxy continues adding mass through star formation and mergers. Each new star that forms will eventually die, perhaps in a supernova that scatters newly synthesized elements through space, continuing the cycle. Those elements will be incorporated into the next generation of stars and planets, perpetuating creation. The cycle continues, slowly increasing chemical complexity throughout cosmic history, building toward ever greater richness. Let's quantify exactly what growing every second means in concrete terms that we can grasp. These numbers help ground abstract concepts in measurable reality, making the invisible visible. Star formation occurs at roughly 1.5 solar masses per year, averaged across the entire Milky Way, integrated over all regions. That's about 2.8 times 10 to the power of 27 kilograms per year. Divided by seconds in a year, roughly 31 million, this gives roughly 9 times 10 to the power of 19 kilograms per second. That's 90 billion trillion kilograms every second, converting from diffuse gas into dense protostellar cores, matter transforming. For comparison, Earth's mass is roughly 6 times 10 to the power of 24 kilograms. So every week, the Milky Way forms roughly 1 Earth mass worth of new stars, an entire planet's worth of matter compressed into stellar furnaces. Every year, about 50 Earth masses. Over 1 million years, about 50 million Earth masses, or roughly 1/8 the mass of Jupiter, substantial accumulation. Satellite galaxy tidal stripping adds mass more slowly but steadily, continuously. The Sagittarius dwarf loses perhaps 100,000 to 1 million solar masses per orbit through tidal forces stripping away its outer layers. Each orbit takes roughly 1 billion years. So on average, the Sagittarius dwarf contributes perhaps 1 to 10 solar masses per year, comparable to star formation rates, but in the form of pre-existing stars being added to the halo rather than new stars forming from gas, a different channel of growth. Gas accretion from the hot halo operates continuously at uncertain rates that remain difficult to measure. Estimates suggest perhaps 2 to 5 solar masses per year of gas cool from the hot halo and fall into the disk where it can eventually form stars. This gas doesn't immediately become stars upon arrival. It may orbit in the disk for hundreds of millions of years before finding itself in a region dense enough to collapse gravitationally. But it represents continuous mass addition that sustains long-term star formation, fuel for the future. Sagittarius A star, the central black hole, accretes roughly 3 times 10 to the power of 20 kilograms per year, based on current luminosity and assuming standard accretion efficiency. That's about 1/10,000th of a solar mass per year, or approximately 5 million kilograms per second, enormous by terrestrial standards. This seems like enormous mass from the perspective of any material falling in, but it's negligible compared to the black hole's total mass of 4.15 million solar masses, barely a snack. At the current accretion rate, Sagittarius A star gains roughly 1 solar mass every 10,000 years. To double its mass through accretion alone would take 40 billion years at this rate, longer than the current age of the universe, an incredibly slow process. Black hole growth is currently slow, but it will accelerate dramatically during the Andromeda merger when disrupted gas floods into the central regions, temporarily feeding the monster. The upcoming Andromeda merger will add roughly 600 to 800 billion stars in one dramatic event, occurring over several billion years of violent interaction. Averaged over that merger timescale, this represents adding perhaps 100 to 200 solar masses per year in stars, roughly 100 times faster than current star formation, a dramatic acceleration. Of course, the mass addition won't be steady, but concentrated during close passages when gravitational interactions are strongest, pulses of growth. Adding everything together from all sources, the current growth rate is roughly 3 to 5 solar masses per year from all sources combined. Over 1 million years, this adds 3 to 5 million solar masses, roughly 1/100th of 1% of the galaxy's current stellar mass, small but measurable. Over 1 billion years, 3 to 5 billion solar masses, roughly 1% of current stellar mass, significant accumulation. But eventually, inevitably, even red dwarfs exhaust their fuel. The last one will die perhaps 10 to 15 trillion years from now, leaving behind a white dwarf that cools over subsequent trillions of years, fading into darkness. By then, Milky Way will be a graveyard of stellar remnants. White dwarfs, neutron stars from ancient supernova explosions, stellar mass black holes, and brown dwarfs that never ignited fusion will orbit silently in the darkness, cold and dead, monuments to a more active past. Even this remnant population won't last forever in the ultra-long term. Gravitational interactions between orbiting objects lead to energy exchange through close encounters. Close encounters can give one object enough energy to reach escape velocity, flinging it into intergalactic space, while the other loses energy and sinks deeper into the gravitational well, a cosmic redistribution. This process, called evaporation, slowly disperses the galaxy over timescales of 10 to the power of 20 years, roughly 10 billion trillion times the current age of the universe, an incomprehensible duration. Computer simulations show that after this evaporation phase, perhaps 1 to 10% of the galaxy's mass remains in a dense core of tightly bound remnants surrounding the central black hole. The rest has been ejected into intergalactic space, doomed to wander alone through an exponentially expanding cosmos where the space between objects doubles every 10 billion years or so, eternal exile. These numbers might seem small as percentages, barely noticeable, but sustained over billions of years, they're substantial and transformative. The Milky Way has likely added 20 to 30% of its current stellar mass over the last 5 billion years through ongoing star formation and satellite accretion, considerable growth. Looking forward, before the Andromeda merger, it will likely add another 5 to 10% over the next 3 to 4 billion years. Then the merger will increase mass by roughly 100% in one dramatic event, doubling the galaxy in one cosmic collision. The Milky Way's growth story is not unique among galaxies. Every large galaxy in the universe formed through similar processes operating across cosmic time. Hierarchical merging assembled mass from smaller structures in bottom-up construction. Gas accretion provided raw material for ongoing star formation, fuel for stellar nurseries. Satellite cannibalism added mass and stars through gravitational conquest. Chemical evolution slowly increased elemental complexity through stellar nucleosynthesis. The processes are universal, even as details vary. But there's enormous diversity in outcomes despite similar processes. Some galaxies, like ours, continue forming stars at modest rates, their blue spiral arms marking ongoing starbirth in glowing nebulae. Others have become red and dead ellipticals, having exhausted their gas supplies billions of years ago, and now filled with aging red stars slowly fading, stellar graveyards. Still, others are undergoing dramatic starbursts, forming stars at 100 or more times the Milky Way's rate, often triggered by recent mergers or interactions, temporary explosions of activity. Galaxy clusters contain thousands of galaxies, all interacting gravitationally and occasionally merging in complex dances. The central regions of massive clusters host enormous elliptical galaxies containing trillions of stars formed through hundreds of mergers over cosmic time, cosmic monsters. These brightest cluster galaxies, as astronomers call them, represent the end state of hierarchical growth, the largest galaxies the universe can produce through gravitational assembly. In voids, those enormous underdense regions between filaments and clusters, small dwarf galaxies drift in isolation far from the main action. Some of these may have experienced little growth since they formed billions of years ago, preserving conditions from the early universe nearly unchanged. They're cosmic fossils, windows into galactic youth frozen in time by isolation, living relics. The cosmic web itself continues evolving on the largest scales. Filaments grow thicker as more matter flows along them, channeled by gravity. Clusters grow more massive as groups fall in and merge, accumulating mass. Voids expand as matter is pulled away toward denser surroundings, emptying further. This large-scale evolution proceeds slowly compared to human timescales, but it continues relentlessly, driven by gravity working on dark matter structures across hundreds of millions of light-years. And underlying everything, dark energy accelerates cosmic expansion. This acceleration is gentle now, noticeable only across distances of billions of light-years where it dominates. But it's relentless and eternal, growing stronger with time as the universe expands. Eventually, perhaps 100 billion years from now, expansion will have pushed all unbound structures beyond the cosmic horizon where they can never be seen again. Each bound system, each merged galactic group, will become an island universe alone in exponentially expanding space, isolated forever. The Milky Way's growth occurs within this cosmic context, part of something far larger. We're part of a vast hierarchical structure spanning the observable universe, one galaxy among hundreds of billions. Our growth through star formation and mergers mirrors processes occurring in countless other galaxies across cosmic distances. Our eventual merger with Andromeda parallels mergers happening throughout the cosmos, a common fate. And our ultimate isolation in a merged local group reflects the fate awaiting all gravitationally bound structures in a dark energy-dominated universe, the final chapter. Growth doesn't last forever for any galaxy. The Milky Way won't continue adding mass indefinitely into an infinite future. Several processes will eventually halt galactic growth and lead to long-term decline, an ending. First, star formation will cease when gas supplies are exhausted, running out of fuel. Even with ongoing gas accretion, total gas mass is finite, limited. Over tens to hundreds of billions of years, gas will be either converted into stars, ejected by stellar feedback from supernovae and stellar winds, or locked in stellar remnants where it can't participate in future star formation. Without gas, no new stars can form, ending the cycle. Star formation rates will gradually decline, dropping below 1 solar mass per year, perhaps 10 billion years from now, then below 1 solar mass per century, then effectively ceasing altogether, the last stellar birth. Second, satellite accretion will end when all nearby satellites have been consumed, eaten by the growing galaxy. The local group contains dozens of known satellites, but this is a finite population, limited and countable. Over the next 10 to 100 billion years, all will be absorbed into Milky Way through tidal disruption. After that, no more satellites remain nearby. The nearest sources of additional mass will be other galaxy groups dozens of millions of light-years away, and dark energy will have pushed them beyond reach, forever inaccessible. Third, dark energy will cut off potential mergers with distant galaxies, isolating us. In a static universe without dark energy, the Milky Way might eventually merge with Virgo or other nearby clusters over timescales of hundreds of billions of years, slowly drawn together by gravity. But in our accelerating universe, structures that aren't yet bound will never become bound despite their mutual attraction. They'll recede faster than gravity can pull them together, pushed apart by expanding space. The cosmic horizon will shrink around Milky Way, cutting it off from potential merger partners, creating ultimate isolation. Within approximately 200 billion years, Milky Way will have completed its growth in all meaningful ways. All local satellites consumed, all major mergers finished, gas supplies exhausted. Star formation ceased. At that point, the galaxy enters its long twilight, a slow fade lasting trillions of years as its stars age and die without new generations to replace them, an irreversible decline into darkness. This end of growth is not unique to the Milky Way. All galaxies will experience similar fates over vast timescales, though timings vary. Small dwarf galaxies may exhaust their gas and cease star formation within the next few billion years, dying young. Giant ellipticals in cluster centers may have already stopped forming stars billions of years ago, already dead. The Milky Way occupies a middle position, with perhaps another 10 to 20 billion years of significant star formation remaining before the final decline begins, a measured fade. Where do we fit into this vast story of galactic growth and evolution? The Sun formed 4.6 billion years ago, roughly 1/3 of the way through the Milky Way's history. The galaxy was already ancient when our solar system was born, containing hundreds of billions of stars and having experienced billions of years of growth and evolution, a mature galaxy. The interstellar cloud, that collapsed to form the Sun was chemically enriched by roughly 9 billion years of previous stellar generations, countless cycles of birth and death. It contained all the heavy elements necessary for rocky planets and complex chemistry the periodic table represented. When the Sun ignited through fusion, the remaining material in its protoplanetary disk coalesced into planets, asteroids, and comets through gravitational accretion. Earth formed within a few tens of millions of years as rocky material clumped together through endless collisions. Life appeared on Earth perhaps as early as 4 billion years ago, within just a few 100 million years of the planet's formation, remarkably quickly. For 3 billion years, life remained microbial, slowly evolving complexity through natural selection. Multicellular life appeared roughly 600 million years ago, a dramatic transition. Complex animals emerged in the Cambrian explosion 540 million years ago, diversifying rapidly. Dinosaurs dominated from 230 million to 66 million years ago. Modern humans appeared less than 300,000 years ago, barely a moment in cosmic time. On galactic timescales, our entire existence is incomprehensibly brief, a fleeting instant. The Milky Way has completed roughly 60 orbits since Earth formed. It's completed about half of one orbit, roughly 100 million years since dinosaurs went extinct. It's completed essentially 0% of an orbit since modern humans appeared, too brief to measure. We're latecomers, arrived near the end of the galaxy's active growth phase after most of its dramatic early evolution was complete, witnesses to maturity rather than birth. But we're here at a special time in cosmic history. Star formation continues, providing the spectacle of nebulae and star clusters we observe throughout the galaxy, beauty in the darkness. Satellite accretion is ongoing, allowing us to witness galactic cannibalism in action, violence unfolding. The Andromeda merger approaches, scheduled to begin in a few billion years, drama ahead. And we've arrived at precisely the epoch when technology allows us to understand what's happening around us, consciousness observing cosmos. We exist at a time when the Milky Way is still active and evolving, but old enough to have produced the chemical complexity necessary for life through billions of years of stellar processing. We exist at a time when advanced technology allows us to observe and understand galactic growth processes operating around us, telescopes revealing secrets. And we exist at a time when the universe beyond our galaxy remains visible and accessible to observation, providing context for understanding our place in cosmic evolution, a window still open. This is not coincidence or divine providence. In a sense, it couldn't have happened much differently given physical constraints. Chemical complexity requires billions of years of stellar nucleosynthesis, time to build the periodic table. Technological civilization requires complex chemistry, silicon for computers and metals for construction. Therefore, intelligent technological civilizations will almost certainly arise during epochs when galaxies are still active but chemically mature, the Goldilocks zone of cosmic time. We're seeing the universe at the time when observing and understanding it becomes possible, consciousness emerging when the cosmos can be comprehended. Let's return to where we started, closing the circle. Right now, while you're reading this, the Milky Way is transforming. Not in some abstract theoretical sense, but measurably, observably, continuously. Somewhere in a molecular cloud in the Orion Arm, a dense core is collapsing right now, Gas that's been drifting for millions of years is finally compressed enough that gravity overcomes thermal pressure. The core will heat up as it shrinks over thousands of years. In a few 100,000 years, it will ignite fusion and become a star, shining. But the collapse is happening now, right this moment, as you read these words. 50,000 light-years away, a star in the Sagittarius dwarf galaxy just crossed through the Milky Way's disk seconds ago. Tidal forces stretched it slightly in the vertical direction while compressing it horizontally, distorting its shape. The effect was tiny, far too small to notice without precise measurements. But it happened just now, one more step in the gradual dissolution of that dwarf galaxy into streams and halo stars. In intergalactic space, 200,000 light-years above the galactic plane, a cloud of primordial hydrogen is falling inward right now, attracted by the Milky Way's gravity. This gas formed shortly after the Big Bang and has never been part of any galaxy pristine material. In a billion years, it will strike the galactic disk and trigger a small burst of star formation. But its journey toward us is happening now, falling through the dark. At the galactic center, a parcel of hot gas spirals slowly inward towards Sagittarius A star at this very moment. It's been orbiting for millions of years, gradually losing angular momentum through turbulent friction. In another million years, it will cross the event horizon and disappear forever into the black hole. But right now, it's still falling, still heating up, still approaching the point of no return, doomed. 2.5 million light-years away, Andromeda continues its approach as you read this sentence. The distance decreases by 3.5 billion kilometers every year. That's 110 kilometers every second. In the seconds since you started reading this script, Andromeda has moved several hundred kilometers closer, narrowing the gap. The collision is inevitable and approaching, tick by tick, kilometer by kilometer, second by second, destiny approaching. All of this is happening simultaneously, continuously, everywhere throughout the galaxy and its surroundings in this moment. The Milky Way is not a static structure frozen in time. It's a dynamic, evolving system, still under construction nearly 13 billion years after it first began forming from smaller pieces. Understanding this transforms how we think about our cosmic home, our place in the universe. The pale band of light stretching across the night sky isn't a frozen relic from the past, unchanging. It's an active construction site, work in progress, a work in progress. A structure that hasn't finished growing and won't finish for billions of years to come, still building. Every photograph of the Milky Way captures a galaxy in the process of change, a snapshot of an ongoing transformation that spans cosmic time from the distant past into the unimaginably distant future. This is our galaxy, our cosmic home, 400 billion stars spread across 100,000 light-years of space. A spiral galaxy with majestic arms wrapped around a central bar. A system embedded in a trillion solar mass dark matter halo, providing gravitational scaffolding, invisible architecture. A structure that's been evolving for nearly as long as the universe has existed and will continue evolving for billions of years to come, far into the future. The Milky Way is growing bigger every second as you sit here, through star formation converting gas into new suns, stellar birth continuing. Through satellite cannibalism consuming dwarf galaxies, gravitational conquest. through gas accretion from surrounding space, replenishment from the void. Through all these processes operating simultaneously and continuously, our galaxy adds mass and complexity, building itself through the patient architecture of gravity operating across cosmic time, slow but inexorable. And we're here to witness it, blessed with consciousness, to observe it with telescopes and detectors, to understand it through physics and mathematics, to recognize that we're not separate observers watching from outside, but participants embedded within an evolving cosmos, part of the story. The atoms in our bodies were forged through the same stellar processes that continue building the galaxy today, stellar alchemy ongoing. We are, quite literally, children of galactic evolution, products of billions of years of growth and transformation written in our very atoms. The Milky Way's story is our story, inseparable. Its growth made our existence possible through chemical enrichment. Its future will unfold across timescales beyond human comprehension, transforming in ways we can predict but never witness, too slow for human eyes. But right now, in this moment, we're privileged to understand what's happening around us in this brief window of time, to grasp the processes shaping our cosmic home, to see the universe not as a static backdrop, but as a dynamic, evolving system of which we're an integral part, forever connected. The galaxy is growing as you breathe. The processes are ongoing right now. And the story continues, written in starlight and gravity, unfolding across the cosmos.